Okay, so we explained the control flow graph and how we can use it to model the program execution using a integer linear programming model. But the other part of our effort has to be on the processor behavior analysis. That is to say, we need to understand the execution time of the individual basic blocks. So we need to know the C of I. Let me go back to a few slides here. So this part, this C of I, so the execution time of this physical block, this physical basic block, this basic block, this block. We need to understand the C of I. It's affected by the process architecture, and one of the important factor is the cache that as part of the processor. We have a very simple example here. We are doing dot product on two vectors. Dot product is to do a element-wise multiplication and accumulate the product. So let's see, we have two floating point arrays, x and y. And the size of the array is n, which is a third argument to this function. And we use result as the accumulation variable. And we have I as the loop iteration variable. So I goes from 0 to n minus 1. And we increment I in every loop iteration. In the loop iteration, we are doing this element-wise multiplication, and then we accumulate the product into this result. And eventually we return the result. So it's a very simple function. Let's just suppose we run this function on a 32-bit processor. And this 32-bit processor has a direct mapped cache that holds two sets. So what we should not call it direct. It should be a set associative cache, holds two sets. We have four floating point per set. We use this cache to store the variable, in our case, x and y, and they are stored contiguously starting at address 0. So let's look at the case, what will happen if n is 2. When n is 2, we have in the array x, we have two floating point numbers. So two floating point numbers. Y also has two floating point numbers. So altogether, 4 floating point numbers. And we assume that these x and y are stored in memory contiguously. So we have first two elements of x, and then right after we have the two elements of y. They are stored together. If you recall, for the cache, we used address to access the cache. We have the lowest B bits are used to access the bytes in the block. So this is the cache we have, and we have each set we have a block set, and we have So this is the block, and we use the set index to find out which set we want to go into look for the blocks. And we use this set index S to determine that. And the rest of the bits are tag bits. So when you access certain variable in the memory, you will tell the processor, okay, this is the address you will need to use to access memory. Then the processor will take this address, segment it into several parts, and using first the set bit to find out the set. And because we use a direct map, so we only have one tag in the set, and that corresponds to the block. And then after these B bits and S bits, the rest of the bits are the tag. So if the tag matches, that means the address you use to access data is already here in this block. If this tag matches with this tag. When you have a match on a tag, we call it a cache hit. And that's good news because the data you're trying to find out is already here. If the tag does not match, or this is an invalid bit to indicating there's nothing here yet, you need to go fetch the actual data from the block, from the memory, and put it into the block. There's some questions. Let's see. Okay, so what is valid? So there's, let me go. The layout is somewhat messed up here. This is the valid instead of valley. So this is valid. So this is the valid bit, one bit to indicate whether this block has valid data or not. This is for indicating at the very beginning there's nothing in the cache yet. So this valid will be set as 0 to indicating there's nothing there. Once you fetched any data and put it into the block, and that valid bit will be set to 1 to indicating there's something. All right, so in our case, what we have here is for every block we have, so here block offset is 4, so that means we have 2 to the power of 4, we have 16 bytes here in this block. Again, 16 bytes here in this block, 16 bytes here in this block. And recall that we have 2 floating point for X, 2 floating point number for Y. So total we have 4 floating point numbers. And that's exactly 16 bytes. So if we have those X0, X1, Y0, Y1, they will be all together here in this one block. Okay. So our question earlier was, for this program, what happens when n is 2? So when n is 2, we're talking about 2 floating point numbers for X. That means X0 and X1. And then same thing for Y, 2 floating numbers in this array Y. So we have Y0, Y1. So total we have 4 floating point numbers, and they take 16 bytes. Suppose there's nothing in the cache yet. So the first axis of X0, because as the first loop, I is 0, so we're gonna multiply X0 with Y0. When we do multiplication, okay, even though it's just one line here, the processor has to do quite a few things. It has to load data from X0, put into the register, and also load data from Y0, put in the register, then do the multiplication. This is when the memory access happens. So X0 will have to be loaded. Let me go back. So because at the very beginning, there's nothing, so the valid bit is set to 0, then we need to load the actual data. So we will load X0 to put it here. And when we load X0, because the way cache operates is in terms of block, so the whole block will be loaded from memory to this cache. So even though the processor only accesses X0, you will have X0, X1, Y0, Y1, all 4 floating point numbers be loaded to the cache. That's why we say the X0 will cause a cache miss. So we'll pull in X0, X1, Y0, and Y1 into the set 0, or one of the set. So all the other 3 subsequent accesses to X1, Y0, Y1, these 3 floating point numbers will be in the cache already when the processor wants to use them. That's good news. That means that's a cache hit. So this is a cache miss, but X1, Y0, Y1 are all cache hit. Okay, do you follow? Any questions? Okay. Now, what happens if when n is 8? So that means we have 2 bigger arrays. X has 8 floating point numbers. Y has also 8 floating point numbers. And what will happen when we do the same thing? We start this for loop, and we're going to multiply X0 and Y0. From just looking at the code, you will think that, oh, it's exactly the same, right? It's the same multiplication, same accumulation, nothing changes except this n is now going to a bigger upper bound for the for loop. Now what will happen is, because when you first load X0, when the cache finds there's a cache miss, it will load a block into the cache from memory. But this time, because X has 8 floating point numbers, so what's after X0, X1 is X2, X3. So the cache miss will cause these 4 floating point numbers from X to be loaded into the cache at set 0. But when you want to access Y0, it will access this location starting at 0 again. And guess what? And because X0, X1, X2, and X3 are in the cache, it's not Y0. You can't find Y0. So the Y0 will also cause a miss, a cache miss. It will pull Y0, Y1, Y2, Y3 into the same set and evicting those 4 floating points from X. Evicting means that the values of X will be actually overwritten using Y, and go back, and this tag bit will be updated using the address coming from the Y. So when n is 8, or any bigger number than 2, it will cause the Y0 to be, loading at Y0 to be a cache miss, and it will kick the X 0, 1, 2, 3 out of the cache. And when the next time, when this loop iteration goes to loop iteration 1, same thing will happen. The cache will find X0 is a miss, so it has to load, and then subsequently kick Y0 out. So there's really no benefit of loading this array one by one, because you always keep evicting the other group of floats out of the cache. So there's really defeat the purpose of using cache to save the memory access time. So that is bad, and that is the reason in this case the executing time will be much longer than the first case when n is 2. There's also more complicated timing anomalies where the branch will cause the instruction cache to become a cache miss. So it will be loading. You'll be loading the so the instruction that has been loaded will have to be discarded because the prediction is wrong. So the block B have to be evicted from the instruction cache, then the execution will be delayed. So this is a more complicated case happening on the instruction cache, where in the previous example we're talking about data cache. But so the point is that caches and cache misses will cause unintended consequences for the execution of the instructions.